Okay, so for this video, we are going to wrap up constraint optimization problems, and we're going to talk about problems with two constraints. So for problems with two constraints, we take a very similar approach to problems with one constraint. Our goal is to find the extremum of a function w as a function of x, y, and z, subject to two constraints, a function g of x, y, z equals 0, and h of x, y, z equals 0. So in this case, we have to worry about two Lagrange multipliers, lambda sub 1 and lambda sub 2. And this time, the gradient of f is going to be a linear combination of the two. So lambda sub 1 times gradient of g plus lambda sub 2 times gradient of h. And of course, the constraint equations. So let's just do an example. We want to maximize x times y times z over the set x plus y plus z equals 30 and x plus y minus z equals 0. So our objective function, right, the thing we're maximizing, apparently I have trouble writing, sorry. So our objective function f of x, y, z is just x times y times z, and our constraints are what? So we can write the first constraint as x plus y plus z equals 30 as x plus y plus z minus 30 equals 0. And so our first constraint function g of x, y, z is x plus y plus z minus 30. And the second constraint is already in the correct form. So our second constraint is h of x, y, z is x plus y minus z. So those are our constraint functions. All right, so now using what we have above, we have that gradient of f is lambda sub 1 times gradient of g plus lambda sub 2 times gradient of h. So gradient of f is just going to be the vector yz, xz, xy. The gradient of g is just going to be the vector 1, 1, 1. And the gradient of h is going to be the vector 1, 1, negative 1. So when we now go to form our system, what are we going to have? So we have the gradient of f being the linear combination of the gradients of g and h. So we're going to get the vector yz, xz, xy is lambda sub 1 times the vector 1, 1, 1 plus lambda sub 2 times the vector 1, 1, negative 1. And then, of course, we have our constraint equations, right? G is equal to 0, so we get x plus y plus z equals 30. And h is equal to 0, we get x plus y minus z equals 0. And doing what we did previously, right, we equate the corresponding components, and we're going to obtain, so the first component on the left is yz, and the first components on the right are lambda sub 1 times 1 plus lambda sub 2 times 1. Second component on the left is xz, and so the second components on the right are lambda sub 1 times 1 plus lambda sub 2 times 2. Finally, the third component on the left is x times y. And on the right, we have lambda sub 1 times 1 plus lambda sub 2 times negative 1. And, we have the constraint equations. Okay, so let's see. Now, let's multiply the first three equations this time. We'll multiply the first by x, the second by y, and the third by z. The advantage here is that we're going to have x, y, z everywhere. So we're going to get x, y, z is equal to x times lambda sub 1 plus lambda sub 2. X, y, z is going to equal y times lambda sub 1 plus lambda sub 2. And x, y, z is going to equal z times lambda sub 1 minus lambda sub 2. So multiplying that gives us okay, now what? So if lambda sub 1 plus lambda sub 2 were equal to 0, then that would mean that x times y times z would equal 0, but we know that's not a maximum. Right? How do we know that? Because we know x times y times z can be positive even for values that satisfy those constraints, like 15, 2, 1. Would that work? That doesn't satisfy those constraints. You know, getting something that does. Sorry about that. But it can be positive. And similarly, right, we know that, or we can say that z is not equal to 0, right, by a similar argument. Okay, so this means, let's say I were to number these equations, I'll call them A, B, and C. Not these equations, sorry. Numbering the wrong equations. Let's try that again. A, B, and C. So our original top three. So we can divide, let's say, A and B by Z, because Z is not 0. And if I do that, I'm going to get y is equal to lambda sub 1 plus lambda sub 2 over z. And also x is equal to lambda sub 1 plus lambda sub 2 over z. Okay, so x is equal to y. All right, now, from constraint 1, I will call that D and E. So from D, sorry, E, D is harder. From E, we have Z is equal to x plus y, but that's just 2x. And now if we substitute into D, what are we going to get? We're going to get x plus 2x equals 30. So 4x equals 30. So x is 30 over 4, or 15 halves. So finally, since x is equal to y, y is also equals to 15 halves, and z is equal to 2x, so z is equal to 15, giving a maximum value for the objective function of f of 15 halves, 15 halves, 15, which is 15 halves times 15 halves times 15, which is 3,375 divided by 4. And that's our maximum. Okay, well, that's actually all we have for constrained optimization. As you can see, you have to be very clever and use various solution techniques, you may call them tricks if you want, to attack these problems and be able to solve them. So unfortunately, that's just kind of the way it is. And I just will leave it to you to play with these. So that makes these kind of interesting problems, and it makes them a little bit more challenging as well. All right, so there are some suggested exercises for you, which will give you extra practice. And until next time, have a great day.